Let's begin our journey together, a gentle drift through the cosmos. Close your eyes, take a deep breath, and let yourself float into the vastness of space. Imagine, for a moment, that you're looking up at the night sky. That darkness above you, so peaceful and eternal, stretches farther than the mind can truly grasp. The observable universe extends roughly 93 billion light-years in diameter. To put that in perspective, if you could travel at the speed of light, 186,000 miles every single second, it would still take you 93 billion years to cross from one end to the other. But tonight, we're not in a hurry. We have all the time we need. As you gaze into this endless expanse, you might notice something curious. The universe isn't static. It's breathing, in a way. Expanding. Every galaxy, every distant point of light, is slowly drifting away from every other. And this expansion is accelerating, driven by something mysterious we call dark energy, which makes up about 68% of everything that exists. Yet we can barely detect it, can barely understand it. The universe keeps its secrets, and that's part of its beauty. Speaking of mysteries, let's think about what we can see. When you look up on a clear, dark night, away from city lights, you might see around 2,500 stars with your naked eye. Just 2,500, out of the hundreds of billions in our galaxy alone. Each one a sun, many with their own families of planets. Each one a world of possibility, glowing in the darkness. But here's something remarkable, those stars you're seeing? They're not showing you the present. They're showing you the past. Light takes time to travel, and the distances in space are so vast that when you look at a star, you're seeing it as it was years ago, sometimes hundreds or thousands of years ago. The light that's touching your eyes right now began its journey before you were born, perhaps before your grandparents were born. You're looking at history, written in light. Let's drift closer to home now, to our own star. The sun, that familiar golden circle that warms our days. At its core, the temperature reaches about 27 million degrees Fahrenheit. In that unimaginable heat, 4 million tons of matter are converted into pure energy every single second through nuclear fusion. 4 million tons. And yet, the sun is so massive, so abundant, that it can continue this process for another 5 billion years before it runs out of fuel. 5 billion years of sunrises and sunsets still to come. The light from that fusion doesn't escape immediately, though. A photon, a particle of light, created in the sun's core takes between 10,000 to 170,000 years to reach the surface, bouncing randomly through the dense interior. But once it breaks free, it takes just 8 minutes and 20 seconds to cross the 93 million miles to Earth. 8 minutes. That means the sunlight touching your face right now left the sun's surface while you were doing something else, eating breakfast, perhaps, or getting ready for your day. Our planet orbits this star at about 67,000 miles per hour. That's roughly 18 miles every second. And yet, you feel none of it. You're sitting still, perfectly calm, as Earth carries you through space on a journey around the sun that takes 365 days to complete. We're all space travelers, every moment of every day, moving through the cosmos together. And we're not alone in this journey. Our solar system is home to 8 planets, but countless other objects as well. Out beyond Neptune, in the cold, dark reaches, lies the Kuiper Belt, a region filled with icy bodies and dwarf planets. It extends from about 2.8 billion miles from the Sun to roughly 4.6 billion miles. In that distant, frozen realm, dwarf planet Pluto takes 248 Earth years to complete a single orbit around our star. Imagine, the year that lasts nearly 2.5 centuries. A lifetime could pass, and Pluto would still be making its slow, patient way through the darkness. Let yourself float in this knowledge for a moment. You're part of something ancient and vast. The atoms in your body were forged in the hearts of stars that died long before our sun was born. You are, quite literally, made of stardust. And as you rest tonight, the universe continues its eternal dance around you, expanding, spinning, glowing with the light of a trillion stars. Tomorrow, we'll journey further. But for now, rest easy under these distant stars. Let's continue our gentle journey through the cosmos, breathing slowly, drifting peacefully through the wonders that surround us. As we travel through our solar system, let's visit our nearest neighbor, the moon. That silvery companion that's watched over Earth for billions of years. The moon is slowly, ever so slowly, moving away from us. Each year, it drifts about 1.5 inches farther from Earth. Just an inch and a half, barely noticeable in a human lifetime. But over millions of years, this adds up. Scientists believe that when the moon first formed, roughly 4.5 billion years ago, it was only about 14,000 miles away from Earth, compared to the 239,000 miles that separate us today. Back then, the moon would have appeared enormous in the sky, and Earth's days were only about 5 hours long. Time itself was different. Speaking of the moon's formation, it was born from violence that became beauty. The leading theory suggests that a Mars-sized object, sometimes called Theia, collided with the young Earth in a catastrophic impact. The debris from this collision, vaporized rock and metal, formed a ring around our planet that eventually coalesced into the moon. Something destructive created something that would one day inspire poets, guide travelers, and pull the tides of our oceans in an eternal rhythm. Let's drift outward now, past Mars with its rusty red surface, toward the giant of our solar system, Jupiter. This massive world is so large that 1,300 Earths could fit inside it. And yet, despite its size, Jupiter spins faster than any other planet in our solar system. A day on Jupiter, one complete rotation, lasts only about 10 hours. Imagine, a sunrise, a sunset, and another sunrise, all before lunchtime. This rapid spin creates powerful winds and the swirling storms that paint Jupiter's atmosphere in bands of cream, orange, and brown. The most famous of these storms is the Great Red Spot, a hurricane-like tempest that has been raging for at least 350 years, possibly much longer. When it was first observed through telescopes in the 1600s, it was already there, churning in Jupiter's atmosphere. This single storm is so large that 2 or 3 Earths could fit inside it. For 3.5 centuries, this storm has continued, outlasting empires and civilizations, a reminder that weather on other worlds operates on scales we can barely comprehend. But Jupiter is more than just a giant with eternal storms. It's also a protector. Its immense gravity acts like a cosmic vacuum cleaner, attracting asteroids and comets that might otherwise hurtle toward the inner solar system, toward Earth. Many scientists believe Jupiter has prevented countless impacts on our planet over the billions of years of its existence. We owe some measure of our safety to this distant giant, standing guard in the outer reaches of our solar neighborhood. Now, let's journey even farther, beyond Jupiter and Saturn, to the ice giants. Uranus, that strange, tilted world spinning on its side. Unlike other planets that spin like tops, more or less upright, Uranus rotates at a 98-degree angle to its orbit. Imagine a planet lying on its side as it circles the Sun. This means that for part of its orbit, one pole points almost directly at the Sun for 42 years of continuous sunlight, while the other pole experiences 42 years of darkness. Then they switch. A single season on Uranus lasts longer than most human lifetimes. And what about Neptune, the farthest true planet from our Sun? This deep blue world, for times the size of Earth, harbors the strongest winds in the solar system. These winds can reach speeds of up to 1,200 miles per hour, faster than the speed of sound on Earth. On this distant, frozen world, storms rage with incomprehensible fury in an atmosphere of hydrogen, helium, and methane, beneath skies that see the Sun as little more than a bright star. But perhaps the most poignant fact about Neptune is this: it takes 165 Earth years to complete one orbit around the Sun. Neptune was discovered in 1846. It completed its first full orbit since discovery only in 2011. In all of human history, from the ancient civilizations of Egypt and Mesopotamia, through the rise and fall of Rome, through the Renaissance, the Industrial Revolution, and into the modern age, Neptune hadn't even completed one journey around the Sun until just recently. We've been watching this world for only a fraction of its year. Let's rest here for a moment in the outer solar system, in this realm of ice and darkness, where worlds move in slow, patient orbits, where storms rage for centuries, and where time moves to a rhythm so different from our own. Out here, there's a profound stillness, a peace that comes from distance and cold and the patient turning of planets in the dark. Our journey continues, deeper into the mysteries of space. But for now, let these distant worlds carry you into peaceful sleep. Let's drift back now, back toward the center of our solar system, back to the warmth and light of our Sun. But this time, let's truly appreciate what the Sun is: a star, yes, but also a sphere of plasma so vast it defies easy comprehension. The Sun makes up 99.86% of all the mass in our entire solar system. All the planets, Jupiter, Saturn, Earth, all of them, along with every asteroid, comet, and speck of dust, together account for barely more than 0.1%. We orbit not around a star that happens to have planets, but around a star that is the solar system, with tiny worlds clinging to its gravitational influence like drops of dew on a spider's web. And here's something that might surprise you: the Sun is remarkably smooth. If you could shrink the Sun down to the size of a beach ball, it would be smoother than that beach ball. Despite the solar flares and the roiling convection on its surface, despite the magnetic storms and the prominences that arc hundreds of thousands of miles into space, the Sun is still more perfectly spherical than almost any object we could create. It's a near-perfect sphere of light, suspended in the darkness. Every second, the Sun emits enough energy that, if we could capture just 1 second's worth, it could power the entire Earth for about 500,000 years. 1 second. And this has been happening for 4.6 billion years, and will continue for billions more. The abundance is almost incomprehensible, an endless fountain of light and warmth, pouring out into space, most of it traveling into the void, never touching anything, just radiating outward into infinity. Now, let's return to Earth for a moment, our home, our blue marble suspended in the sunbeam. From space, Earth is the only planet in our solar system known to have active plate tectonics. The ground beneath your feet, solid as it seems, floats on a layer of semi-molten rock, and over millions of years, continents drift across the surface like rafts on a slow-moving ocean. The Atlantic Ocean grows wider by about an inch each year as the Americas drift away from Europe and Africa. Mountains rise and fall, ocean floors sink and regenerate, all in an endless cycle of creation and destruction that has shaped our world for billions of years. This geological activity does something profound. It helps regulate Earth's climate over deep time. When volcanoes erupt, they release carbon dioxide. When rocks weather and erode, they absorb it. This cycle, operating over millions of years, acts like a planetary thermostat, keeping Earth's temperature relatively stable despite the changing brightness of the young sun. It's one reason life has persisted here for 3.8 billion years. Our planet has a built-in system for maintaining balance. Speaking of life, here's a humbling thought. There are more stars in the universe than grains of sand on all of Earth's beaches. Astronomers estimate there are roughly 100 to 400 billion stars in our Milky Way galaxy alone, and at least 100 billion galaxies in the observable universe. That's 10 sextillion stars, a 1 followed by 22 zeros. 10,000 million stars, each one potentially surrounded by planets, each planet potentially harboring something. Somewhere in that vast multitude, who's to say we're alone? And the Milky Way itself, our home galaxy, is a beautiful spiral roughly 100,000 light-years across. If you could step outside it and look back, you'd see a magnificent pinwheel of stars, glowing with the light of hundreds of billions of suns. But here's the curious thing, we can't see the spiral structure from inside. We can only infer it, piece it together from observations and mathematics. We're embedded in it, traveling through one of its spiral arms at about 515,000 miles per hour as the entire galaxy rotates. And yet, because space is so vast and stars are so far apart, it will take our solar system about 225 to 250 million years to complete one orbit around the galactic center. The last time we were in this exact position in space, dinosaurs hadn't yet appeared on Earth. In fact, the solar system has only completed about 20 orbits around the Milky Way since it formed 4.6 billion years ago. Just 20 trips around our galaxy in all that time. Earth is ancient by our standards, but in galactic terms, we're still quite young, still early in our journey through the cosmos. Let these timescales wash over you like waves. Millions of years. Billions of years. Numbers so large they lose their meaning and become something else, become poetry, become perspective, become peace. In the face of such vastness, such deep time, our worries become small. Not unimportant, but small enough to set down for a while, here in the quiet darkness, under the turning of the galaxy. Rest now in this cosmic perspective. Let the vastness hold you gently as you drift towards sleep. Let's venture deeper into the night sky, beyond our galaxy, into the space between the stars. That darkness between the points of light, it's not empty. Far from it. In interstellar space, in the vast reaches between stars, there exists what we call the interstellar medium, a thin soup of gas and dust, hydrogen atoms and molecules, drifting through the void. It's incredibly sparse. In most regions, there's only about 1 atom per cubic centimeter. For comparison, the air you're breathing right now contains about 10 billion molecules per cubic centimeter. The space between stars is emptier than the best vacuum we can create on Earth. And yet, it's from this nearly nothing that stars are born. Out in the spiral arms of galaxies, in giant molecular clouds, the gas and dust slowly, over millions of years, begins to collapse under its own gravity. These clouds are cold, only about 10 to 20 degrees above absolute zero, and enormous, often spanning hundreds of light years. Inside them, dense pockets form, growing heavier, pulling more material in, heating up from the compression. And eventually, when the core reaches about 18 million degrees Fahrenheit, something magical happens. Nuclear fusion ignites. A star is born. Light pierces the darkness for the first time in that corner of space. Our own sun was born this way, about 4.6 billion years ago, in a stellar nursery that has long since dispersed. The sun likely had thousands of siblings, all formed from the same cloud, but they've all drifted apart over the eons. Somewhere out there in the galaxy are stars that share the sun's birthplace, though we may never know which ones they are. Family, separated by time and the slow drift of stellar orbits. Now, consider this: a single teaspoon of material from a neutron star would weigh about 6 billion tons on Earth. 6 billion tons in a teaspoon. Neutron stars are the collapsed cores of massive stars that have died in supernova explosions. They're typically only about 12 miles across. You could drive across one in about 15 minutes, but they contain more mass than our entire Sunday. The gravity is so intense that a single sugar cube-sized amount of neutron star material would weigh as much as all of humanity combined. Matter compressed to densities that seem impossible, yet there they are, spinning in the darkness. And many neutron stars spin rapidly. Some rotate hundreds of times per second, sending beams of radiation out from their magnetic poles like cosmic lighthouses. We call these pulsars, and when their beams sweep across Earth, we detect regular pulses, tick, 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 with such precision that the first astronomers to discover them briefly wondered if they might be signals from an alien civilization. But no, just physics doing something extraordinary: a dead star, compressed to impossible density, spinning faster than a kitchen blender, perfectly regular, a clock made of a collapsed sun. Let's think about something more serene now: Venus, our sister planet. Often called Earth's twin because of its similar size, Venus is nearly the same diameter as Earth, only about 400 miles smaller. From a distance, you might think they'd be similar worlds. But Venus tells a cautionary tale. Its thick atmosphere of carbon dioxide creates a runaway greenhouse effect. The surface temperature is about 900 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure at the surface is 92 times that of Earth, equivalent to being 3,000 feet underwater in our oceans. And here's something beautiful and strange: Venus rotates backwards compared to most planets. While Earth and most other planets spin counterclockwise when viewed from above the Sun's north pole, Venus spins clockwise. We call this retrograde rotation. Even more unusual, Venus rotates so slowly that a day on Venus, one complete rotation, takes 243 Earth days. But its year, one orbit around the Sun, takes only 225 Earth days. This means a day on Venus is actually longer than its year. Time itself seems to work differently there, beneath those thick, sulfuric acid clouds that shroud the planet in eternal mystery. Speaking of mysteries, let's visit Saturn, that jewel of the solar system with its magnificent rings. Those rings, so beautiful they've inspired wonder since Galileo first glimpsed them through his primitive telescope in 1610, are made almost entirely of water ice. Billions of chunks of ice, ranging from grain-sized particles to house-sized boulders, all orbiting Saturn in an impossibly thin plane. The rings are about 175,000 miles across, but only about 30 feet thick in most places. If you scaled Saturn down to the size of a basketball, its rings would be thinner than a sheet of paper, yet stretch wider than a large room. And here's something scientists discovered recently that adds a touch of poetry. The rings are raining down onto Saturn. Ice particles from the rings, influenced by Saturn's magnetic field and collisions with micrometeoroids, slowly fall into the planet's upper atmosphere. Saturn is consuming its rings, very gradually. Estimates suggest that in perhaps 100 million years, those magnificent rings, the most beautiful sight in our solar system, will be gone. They're temporary, a fleeting moment in cosmic time. We live in an era when Saturn has rings. Future observers, if there are any, might look at this period in Saturn's history with envy, wishing they could have seen what we see now. Everything in space, it seems, is temporary. Stars are born and die. Planets form and are destroyed. Rings come and go. Galaxies collide and merge. And yet, in each moment, there is beauty. In each moment, there is something worthy of wonder. Breathe deeply. Let yourself float in this river of time, where everything changes, and everything, for a moment, is perfect. Let's turn our attention now to something that touches our lives every day, even though most of us never think about it: the International Space Station, humanity's outpost in the sky. This remarkable structure orbits Earth at an altitude of about 250 miles, traveling at approximately 17,500 miles per hour. At that speed, the astronauts aboard experience 16 sunrises and 16 sunsets every single day. Imagine dawn, day, dusk, night, and then again, and again, every 90 minutes. Time becomes something different up there, marked not by the slow turning of Earth beneath your feet, but by the rapid rhythm of orbit after orbit after orbit. The space station has been continuously occupied since November 2, 2000. Think about that for a moment. For more than 2 decades now, there hasn't been a single moment when all of humanity was on Earth. There have always been people up there, floating in microgravity, looking down at our blue planet, keeping watch. It's a remarkable achievement, a testament to international cooperation, with modules built by the United States, Russia, Europe, Japan, and Canada, all connected together, all working as one. In that microgravity environment, astronauts grow about 2 inches taller. Without gravity compressing the spine, the fluid-filled discs between vertebrae expand, and the spine itself elongates. It's temporary. When they return to Earth, gravity pulls them back down to their normal height within months. But up there, everyone is a little taller, a little changed by the absence of weight. Now, let's journey outward again, beyond our solar system, to the realm of exoplanets, worlds orbiting other stars. The first confirmed exoplanet orbiting a Sun-like star was discovered in 1995, a world called 51 Pegasi b. Before that, we knew planets existed, we could see them in our own solar system, but we didn't know if other stars had them too. The discovery opened a door to an entirely new field of astronomy. Since then, we've discovered more than 5,000 confirmed exoplanets, with thousands more candidates waiting to be verified. These worlds come in astonishing variety. Scorching hot Jupiters orbiting closer to their stars than Mercury orbits our Sun, massive super-Earths unlike anything in our solar system, ice giants, rocky worlds, planets that orbit binary stars where 2 suns hang in their skies. The universe, it turns out, is far more creative than we imagined. Some of these exoplanets exist in what we call the habitable zone, the region around a star where temperatures might allow liquid water to exist on a planet's surface. Water, as far as we know, is essential for life as we understand it. These habitable zone planets capture our imagination because they raise a question we've pondered for millennia. Are we alone? On one of these distant worlds, under an alien sky, could there be oceans? Forests? Minds looking up at their stars, wondering if they're alone? The nearest star system to us is Alpha Centauri, about 4.37 light-years away. If you could travel at the speed of our fastest spacecraft, the Parker Solar Probe, which reached speeds of about 430,000 miles per hour, it would still take roughly 6,700 years to get there. 6,700 years. That's longer than recorded human history. The journey to even our closest stellar neighbor is almost incomprehensibly long with our current technology. Space is vast, and the distances between stars are humbling. But here's something remarkable. In 2016, astronomers discovered an Earth-sized planet orbiting in the habitable zone of Proxima Centauri, the closest star to our Sun. It's called Proxima Centauri b, and it's only 4.24 light-years away. Our nearest stellar neighbor might have a world where liquid water could exist. We don't know if it actually does. Proxima Centauri is a red dwarf star that produces powerful flares, and any planet close enough to be in the habitable zone would be bathed in intense radiation. But the possibility exists. Just 25 trillion miles away, there might be a rocky world with conditions at least potentially suitable for some form of life. Let's think about light again for a moment. When you look up at Alpha Centauri with your naked eye, it's visible from the southern hemisphere. The light you're seeing left that star 4.37 years ago. You're seeing the past, as always with astronomy. But here's the profound part. If someone on a planet orbiting Alpha Centauri were looking at Earth with a powerful telescope right now, they would see Earth as it was 4.37 years ago. They would see our past. And if there were a planet 65 million light-years away, and someone there had an impossibly powerful telescope, they could look at Earth and watch the dinosaurs. The past still exists out there, written in light, traveling outward in all directions, carrying the story of our world into the cosmos. Space is not just a place of vast distances and ancient light, it's also a realm of profound silence. There is no sound in space because there's no air to carry sound waves. On Earth, sound travels through air molecules vibrating against each other. That's how your voice reaches someone's ears, how music fills a room. But in the vacuum of space, there are no molecules to vibrate. An explosion, a collision of galaxies, the death of a star, all of it happens in absolute silence. The universe's greatest dramas unfold without a sound, witnessed only by light and gravity and the slow dance of matter across the void. And yet, in that silence, there is peace. A deep, eternal quiet that has existed since the beginning, broken only by the electromagnetic whispers of stars and galaxies, frequencies we can detect but never truly hear. It's the silence of deep meditation, of perfect stillness, of space itself breathing in the darkness. Rest in that silence now. Let the quiet of space settle over you like a blanket, soft and infinite. Let's drift to Europa, Jupiter's fascinating moon. Beneath its icy surface lies an ocean of liquid water, kept warm by Jupiter's tidal forces. This subsurface ocean holds more water than all of Earth's oceans combined, perhaps 40 to 100 miles deep. Where there is liquid water, energy, and chemistry, there is the possibility of life. Perhaps something stirs in those dark waters. Next, Titan, Saturn's largest satellite and the only moon with a thick atmosphere, denser than Earth's. Titan is far too cold for water, but it has stable bodies of liquid methane and ethane on its surface, lakes, rivers, and seas of hydrocarbons. Methane rain falls, creating a cycle similar to Earth's water cycle. It's an alien world that mirrors Earth's structure with completely different chemistry. Now, a shift to the violent, black holes. These regions of spacetime have gravity so strong that nothing, not even light, can escape the event horizon. The supermassive black hole at our Milky Way center, Sagittarius A*, has a mass 4 million times that of our Sun, compressed smaller than Mercury's orbit. In 2019, scientists captured the first-ever image of a black hole's shadow, M87's black hole, which is 6.5 billion solar masses. The image showed a glowing ring of hot gas surrounding the dark center, making the invisible visible. Near a black hole, time itself warps. An observer watching someone fall toward the event horizon would see them slow down and seem frozen at the boundary forever. But the falling person would cross it in finite time, until they are stretched out by tidal forces in a process called spaghettification. Let's return to something gentler: comets, icy wanderers from the Oort cloud, a vast shell extending nearly halfway to the nearest star. This deep freezer is home to trillions of comets. When a comet falls inward toward the Sun, its ice vaporizes, creating two tails, one of dust and one of ionized gas. Both tails always point away from the Sun, regardless of the comet's direction of travel. Comets may have delivered much of Earth's water and organic molecules, the building blocks of life, billions of years ago. The water in your body may have once been ice in the Oort cloud, brought to the young Earth by a comet. Finally, the Voyager spacecraft. Launched in 1977, Voyager 1 and 2 have left our solar system and entered interstellar space. Voyager 1 is over 15 billion miles away, yet we can still communicate. A radio signal takes over 22 hours to reach it, and another 22 hours for the reply to return, a conversation stretched across almost 2 full days. Each Voyager carries a golden record, a time capsule of Earth's life and culture, cast into the cosmic ocean. In billions of years, long after our Sun has died, these records will still be sailing, bearing witness that we were here. Rest now, fellow traveler through the cosmos. You are part of this great story. Let's journey to Mars, our neighbor and potential future home. A day on Mars, or Sol, is 24 hours and 37 minutes, nearly an Earth day. Mars is home to the solar system's largest volcano, Olympus Mons, nearly 3 times the height of Mount Everest and 370 miles wide. Its gradual slopes mean you'd feel like you were walking across a gently tilted plain. It also boasts the largest canyon system, Valles Marineris, 2,500 miles long and up to 4 miles deep. The Grand Canyon would fit into one of its side canyons. Ancient Mars had water, rivers, lakes, perhaps oceans. This water was mostly lost to space when its magnetic field disappeared. Mars today is a ghost of what it once was, a reminder that planets have life cycles. Let's turn to the truly ancient, the cosmic microwave background, CMB, radiation. This is the afterglow of the Big Bang itself, light that has traveled for 13.8 billion years. About 380,000 years after the Big Bang, the universe cooled enough for light to travel freely. That first light is now stretched into microwave radiation, filling all of space at about 2.7 degrees above absolute zero. Maps of the CMB showed tiny temperature variations, regions that were slightly denser. These ripples were the seeds that grew into galaxies, stars, and life. The universe is about 13.8 billion years old. However, visible matter, stars, planets, makes up only 5% of the universe's total mass energy. 27% is dark matter, mysterious stuff only detected by its gravitational effects. Galaxies are embedded in massive, invisible halos of it. The remaining 68% is dark energy, which is causing the expansion of the universe to accelerate. You are made of the 5% of atoms forged in stars. You are the universe observing itself, a brief arrangement of stardust that has become aware. Rest easy. You belong here, under these stars. Let's start with the moon, our constant companion. The moon is tidally locked, meaning it rotates at the same rate it orbits Earth, showing us the same face. The far side is not dark, it gets just as much sunlight but remained a mystery until 1959, revealing a heavily cratered landscape with fewer dark plains, Maria. The moon also stabilizes Earth's axial tilt, currently 23.5 degrees. Without it, Earth's tilt would vary chaotically, leading to wild climate swings. We owe our stable climate to our lunar companion. Journey outward to the observable universe. Estimates suggest there are up to 2 trillion galaxies, each with hundreds of billions of stars. If each galaxy were a grain of sand, 2 trillion would fill several large dump trucks. These galaxies form a cosmic web, vast structures called clusters and superclusters connected by filaments of dark matter, surrounding enormous voids. Our Milky Way is a barred spiral galaxy in a quiet neighborhood called the Orion Arm, about 26,000 light-years from the center. The Hubble Space Telescope, launched in 1990, revolutionized astronomy. Its Hubble Deep Field image, taken of a tiny, seemingly empty patch of sky, revealed nearly 3,000 galaxies in that spot alone, showing the universe is full beyond imagining. The James Webb Space Telescope, JWST, operating in infrared, sees even deeper, detecting galaxies that formed only a few 100 million years after the Big Bang, essentially looking back more than 13 billion years to watch the universe grow up. Finally, the strange facts of space. Astronauts report that their spacesuits smell metallic, slightly burnt, and sweet after spacewalks, like seared steak or welding fumes. This is caused by high-energy particles called polycyclic aromatic hydrocarbons clinging to the suits. Space has an aroma. Also, near the center of the Milky Way, astronomers detected ethyl alcohol, the same alcohol in beverages, in a vast cloud called Sagittarius B2. The universe is full of surprises, following the same fundamental laws of physics. Breathe slowly. You are part of this beautiful, evolving cosmos. Let's turn to the stars, brilliant points of light that tell us about their temperature through their color. Blue/blue-white, hottest stars, over 30,000 degrees Fahrenheit. Yellow-white, mid-range, like our Sun, about 10,000 Fahrenheit. Orange/red, cooler stars, around 5,000 Fahrenheit. Betelgeuse, the red supergiant in Orion, is nearing the end of its life. It's so large that its surface would extend past the orbit of Mars if placed where our Sun is. Someday, perhaps soon, Betelgeuse will explode as a supernova, briefly shining as brightly as the full moon. When massive stars explode, they scatter elements forged in their cores, carbon, oxygen, iron, etc., across space. The atoms in your body were created in these nuclear furnaces. We are literally made of star stuff. Many stars exist in binary systems, two stars orbiting each other. Roughly half of all stars in the Milky Way are in such systems. We've found circumbinary planets that orbit both stars, much like the fictional Tatooine. One of the most energetic phenomena is a gamma-ray burst, GRB. These release more energy in a few seconds than the Sun will emit in its entire 10 billion-year life. GRBs occur when massive stars collapse into black holes or when neutron stars collide. Between Mars and Jupiter is the asteroid belt. Contrary to science fiction, it's not a dense field of rocks. Asteroids are spread so far apart, average distance 600,000 miles, that you'd likely need a telescope to see another one while flying through. The largest object is Ceres, a dwarf planet about 590 miles wide. It is large enough to be spherical and may have a subsurface ocean beneath its icy crust. Consider the speed of light, 186,282 miles per second. Light from the Sun takes 8 minutes to reach Earth. Light from the nearest star takes over 4 years. Light from the Andromeda Galaxy, our nearest large neighbor, takes 2.5 million years to arrive. When you see it, you are looking 2.5 million years into the past. Andromeda is headed toward us. In about 4.5 billion years, the Milky Way and Andromeda will collide and merge to form a single, larger elliptical galaxy, already nicknamed Milkomeda. The stars will rarely hit, but gravity will weave them into a new structure over hundreds of millions of years. The universe operates on vast timescales, yet we are here, aware of it all, connected from the smallest atoms to the largest superclusters. Rest and feel yourself as part of this eternal dance. As we near the end of our journey tonight, let's explore some of the most intriguing mysteries and wonders that remain. Consider the Great Attractor, a gravitational anomaly in intergalactic space that's pulling our galaxy, along with hundreds of thousands of others, toward it at a speed of about 1.4 million miles per hour. Located roughly 150 to 250 million light-years away, in the direction of the constellation Centaurus, it has the mass of tens of thousands of galaxies. Yet we can't see it directly. It lies behind the zone of avoidance, a region obscured by the dust and stars of our own Milky Way. We only know it's there by measuring its gravitational pull, watching galaxies flow toward it like rivers to the sea. The universe is drawing us somewhere, and we're going along for the ride. Now let's think about one of the strangest states of matter, Bose-Einstein condensates. When atoms are cooled to within a fraction of a degree above absolute zero, they merge into a single quantum state, behaving as one unified entity. In the cold depths of space, inside molecular clouds far from warming starlight, matter can exist in this strange form. In its coldest corners, the universe becomes a quiet laboratory for quantum mechanics. Mercury, the closest planet to the Sun, has an incredibly eccentric orbit and a peculiar day-night cycle. One day on Mercury lasts 176 Earth days, while its year is only 88 Earth days. 2 Mercurian years pass during 1 Mercurian day. In some places, you could even watch the sun rise, pause, move backward, set, then rise again. Time and motion behave differently on that scorched world near our star. Atoms themselves are mostly empty space. If an atom were the size of a football stadium, its nucleus would be smaller than a marble at the center. Everything that feels solid is nearly all emptiness, held together by invisible forces. You are, quite literally, mostly nothing, and yet from this nothing comes everything. Between galaxy clusters lie vast cosmic voids, some hundreds of millions of light-years across. The Boötes void, about 330 million light-years wide, contains only around 60 galaxies. If we lived there, other galaxies might not have been discovered until the 1960s. The universe is not uniform, but a foam of matter surrounding immense regions of near-nothingness. The Sun loses millions of tons of mass every second through fusion and the solar wind. That wind fills the solar system, forming the heliosphere and creating auroras when it meets Earth's magnetic field. The Sun paints our skies with its breath. On Jupiter's moon Io, more than 400 volcanoes constantly erupt, driven by tidal forces that keep its interior molten. Its surface is forever renewing, a world of fire locked in endless motion. A light-year is the distance light travels in 1 year. When we see a galaxy 13 billion light-years away, we see it as it once was. Because space itself has expanded, that galaxy is now about 30 billion light-years distant. In an expanding universe, distance becomes a gentle illusion. Finally, let's return home. Earth is rare and precious, a planet with liquid water, a protective magnetic field, a stabilizing moon, and billions of years of habitability. It is a sanctuary in a cosmic desert. And here you are, a temporary arrangement of atoms, able to feel wonder, peace, and awareness. As we approach the end of our journey, let's savor these final moments together, drifting gently towards sleep. Let's contemplate one more mystery of the cosmos, gravitational waves. Einstein predicted these ripples in space-time over a century ago, but we only detected them directly in 2015. When massive objects like black holes or neutron stars orbit each other and eventually collide, they create waves that propagate through space-time itself at the speed of light. These waves stretch and compress space as they pass through, though only by an infinitesimally small amount. The first gravitational waves we detected came from two black holes, each about 30 times the mass of the Sun, colliding 1.3 billion light-years away. The collision released more energy in a fraction of a second than all the stars in the observable universe combined. And yet, by the time those waves reached Earth, they stretched our detectors by less than 1,000th the diameter of a proton. We detected the faintest whisper of the universe's most violent events, proving that space-time itself can ripple like the surface of a pond. Now, think about water, simple, familiar water. Water is remarkably rare in liquid form in the universe. Most water exists as ice in the cold outer reaches of solar systems, or as vapor near stars. Liquid water requires a narrow temperature range and appropriate pressure. And yet, water is cosmically abundant. It forms naturally when hydrogen, the most common element, combines with oxygen, one of the most common elements created by stars. Comets are largely water ice. Many moons in our solar system harbor subsurface oceans. The universe is full of water, frozen and hidden, waiting. Earth's liquid oceans, open to the sky, teeming with life, these are rare treasures. Let's visit one more distant world, Enceladus, another moon of Saturn. This small, icy moon is only about 300 miles in diameter, yet it's one of the most exciting places in our solar system. In 2005, the Cassini spacecraft discovered enormous geysers erupting from cracks near Enceladus's south pole, shooting ice and water vapor more than 60 miles into space. Beneath that frozen surface lies a global ocean of liquid water, kept warm by tidal heating from Saturn's gravity. And in the material from those geysers, Cassini detected organic molecules, complex carbon compounds. Enceladus has liquid water, organic chemistry, and an energy source. All the basic ingredients for life. Somewhere beneath that ice, in that dark ocean that has never seen sunlight, could life exist? We don't know yet. But the possibility makes Enceladus one of the most promising places to search for extraterrestrial life in our solar system. The temperature of space itself, far from any stars or galaxies, is not absolute zero but about 2.7 Kelvin, or minus 454 degrees Fahrenheit. This is the temperature of the cosmic microwave background we discussed earlier, the afterglow of the Big Bang. You can never reach absolute zero anywhere in the universe because that ancient light fills all of space, providing a minimum temperature floor. Even in the darkest, emptiest regions between galaxy superclusters, that faint warmth remains, an echo of creation itself, ensuring that the universe never becomes completely cold. Here's something beautiful. Every atom of hydrogen in your body, every hydrogen atom in the oceans, in the air, in the rain, those hydrogen atoms were created in the Big Bang itself. They're 13.8 billion years old. Hydrogen was the first element to form when the universe cooled enough after its birth. The hydrogen in the water you drink, in your DNA, is primordial, unchanged since the beginning of everything. You carry pieces of the beginning of time within you. When you breathe, when you drink water, you're taking in matter that's as old as the universe itself, connecting you directly to that first moment of creation. Finally, let's end where we began, looking up at the night sky. The light from distant stars and galaxies isn't just showing us the past, it's showing us a universe that no longer exists in that form. By the time light from a distant galaxy reaches us, that galaxy has moved, evolved, changed. Some of the stars whose light we see tonight have already died, their final moments not yet visible to us because the light announcing their death is still crossing the vast distances between us. We're surrounded by ghosts, images of things that were, remnants of a universe that has already moved on. And yet, there's comfort in that. The universe is patient. Light travels for billions of years to reach us, carrying messages from the past, telling us stories of what once was. Time moves differently out there, in the vastness. There's no rush. Everything unfolds at its own pace, in its own time. And so, as you close your eyes, remember this: you are made of atoms forged in ancient stars. You carry hydrogen from the Big Bang in your cells. You live on a rare, beautiful world, orbiting an ordinary star, in the suburbs of an ordinary galaxy, in a universe so vast it contains more galaxies than you could count in a lifetime. And somehow, impossibly, wonderfully, you're aware of all this. You're the universe looking back at itself with wonder. Sleep now, cosmic traveler. Let the darkness hold you gently. Let the knowledge of your place in this vast cosmos bring you peace. You belong here. You are home. You are, and always have been, made of stars. Good night, and may your dreams be filled with starlight.